All right, good afternoon, grade nines. I hope that you guys are all doing well and that you've had a productive week so far, guys. It's time for the grade nine lesson of the week, guys, the 22nd lesson of the year. So, we're back again as expected, and today we are going to be looking at some geometry that's very important for you guys. The reason why we want to look at geometry now, especially at the moment, is because a lot of you are writing your exams, and many of you still have your maths paper two to write. And maths paper two is the one, as I'm sure you know, that includes all of your geometry and probability and so on and so forth. So, in today's lesson, guys, we want to tackle exactly that. We want to look at geometry. We're specifically, going to be looking at the reflection, rotation, translation, and dilation of shapes on a grid in the world of geometry. Okay, so guys, this is a section that is quite important because it translates into the work that we're going to be doing, especially at grade 10 level, where we start looking at the different graphs that you guys have been learning about. There are more than just the two or three that you guys are aware of that you will start learning about in more detail now in grade 10 and onwards. But when we look at these different graphs that we learn about, whether it's straight line graphs, parabolas, logarithmic graphs, and so on and so forth. We will often run into a situation where we need to learn how to reflect these different graphs, right? For a variety of different reasons. It can be for the sake of inverse functions, it can be just for the sake of reflecting graphs. And you'll see how that sort of plays into the work that you guys learn about as you go through the topic of functions at grade 10 level. But, guys, I'm going to start by sharing my screen with you because we have a lot to get through. There's quite a bit of theory that we want to look at, and then we'll take a look at just a few examples towards the end of today's lesson. But on your screen, you should be able to see me scribbling in five different colors. If you guys cannot see that, or you end up having a bit of trouble hearing what I'm saying at any point during the lesson, you need to please let me know so that I can try and fix some of that. Okay, so today's date is the 18th of June. If you'd like to write it down, I would recommend that you guys take notes, especially for the first section of this lesson, which is going to be all of the theory. If you don't want to do the drawing in the second half, I can understand that, but I would recommend you try and take as many notes as possible. Today, we are talking about transformation geometry. Okay. So, guys, I'm really not going to waste any of your time today. If people still intend on joining, they're just going to have to join us as they get the opportunity to do so. But for those of you that are here, we are just going to get started with our work. Okay. So, right. So, guys, what is the world of transformation geometry? Well, when we look at different kinds of 2D shapes that we are working with, we know that we have a section in the world of maths called measurement, right? Which deals with all of those topics like area, perimeter, surface area, volume, and so on and so forth. And when we go through this topic of measurement, we are discussing both 2D and 3D shapes. Now, when we work on a grid like we do with our graphs, we often work on some form of a Cartesian plane or coordinate grid. So this is a great example of something like that. Right. Sorry, guys, I just want to make the background a little darker. Okay, so you guys should be able to see the grid now pretty easily. And what's important about this grid is that we generally work with 2D shapes on this grid, right? So we can be given a triangle, for example, but there is theoretically nothing stopping us from also working with 3D shapes. Now, at grade 9 level, we are not so focused on working with 3D shapes on these grids just yet. So we are just going to pay attention to 2D shapes. Now, if I have a shape on a grid like this, some kind of coordinate grid or Cartesian plane, we have spent quite a lot of time practicing how to identify the coordinates of different points, right? So, for example, this top point of our triangle is at the coordinate -5, 6, just as an example. The bottom right coordinate is at -2, +3, and this one doesn't lie perfectly on the grid, so I'm not going to worry about that for now. What we need to understand about these 2D shapes, grade nines, sorry, is that there's a few different processes that these shapes can undergo. We can take the shape that we have right over here and now enlarge our shape, which changes the coordinates of the different points along the outline of our shape. We can also take this shape and translate it, which means to quite simply move the shape. We can take this shape over here and we can reflect it over the axes that we've just learnt about over the course of grade 8 and grade 9. So in this case, we have the x-axis and the y-axis. So I could be asked to take this shape and create a reflection of the shape about the y-axis. So I would have something that looks like this over here, right? We also have the ability to take a given shape and rotate it by a certain number of degrees in a specific direction. So all of these are what we call transformations, right? A transformation means that a shape undergoes some kind of change. So there are four independent transformations that our 2D shapes can undergo. A, our shape can undergo reflection. Our shape can undergo rotation. It can also undergo translation. And finally, it can undergo dilation. So we need to understand what these four processes mean for a shape, right? What is a reflection transformation? What is a translation, a dilation? And we're going to discuss each of these today in its fair share of detail, and then just take a look at what these transformations look like for specific 2D shapes in the context of a grid or a Cartesian plane. So now what we see happening, grade nines, at your level is that we have um, 2D shapes that we've discussed that are now taken from the topic of geometry and are being weaved into the world of coordinate planes, right? Grids, which we often see in functions, in graphs. So these two topics are now sort of working their way together, and we need to understand how our grids, how our coordinates are all affected when we reflect, rotate, translate, or dilate a 2D shape. So we're going to start right at the very beginning, and we're going to start with reflection of 2D shapes. Okay, please keep in mind we are only working with 2D shapes for the time being. So I would suggest you guys quickly write this down, and I'm going to start writing some notes for you under reflection. Then we'll discuss it and take a look at an example. Please keep in mind, grade nines, that if you guys have any questions, you are more than welcome to ask. I am happy to answer any questions that you guys have. So please don't hesitate to put messages into the comment box for me to answer for you. All right. So a reflection means that we are taking a shape and creating a mirror image of that shape about a line of reflection. Okay, so when we take a shape, grade grade nines, and we choose to reflect it, we can reflect a shape about a few different lines. About just means over. I could be working with a vertical line of reflection, right? In which case I would mirror the shape to be over here. We can also work about a horizontal line of reflection, meaning that my shape would reflect down here. But there's one last line of reflection that a lot of people forget about, and that is our diagonal line of reflection, which would look something like this over here. Okay. Now, in the context of the grids that we work with, the Cartesian plane normally, these different lines of reflection have got different names, right? And it's names that you're familiar with, but you need to make a connection between the two different names. So, right. about a line of reflection, guys, in the very first sentence that we wrote down, please in brackets make sure that you include an abbreviation for the sake of note taking. A line of reflection can be abbreviated to LOR. So we can work with a vertical line of reflection, okay, which means a line heading from top to bottom, up and down. This is usually, not always, but usually the y-axis. Okay. Point B, we can also reflect something over a horizontal line of reflection. Now, if we think about the most prominent horizontal line on a Cartesian plane, we are usually talking about the x-axis, but it's not always the case that this is the line that we are reflecting over. Okay, and C, finally, there is the diagonal line of reflection. Please keep in mind, grade nines, that this is going to be a lesson that is split over 2 separate sessions because there's quite a lot to go through. So when we reflect a shape, it's important to remember that we're trying to create a mirror image. Okay. I'm going to give you guys 1 minute to quickly copy, and then I'm going to go and draw some examples. Okay. So let's go and take a look very quickly. If I have a grid over here, it's quite clear, guys, that the prominent horizontal line is our x-axis, which I could reflect over. And it's also possible to reflect about the y-axis too, which is the prominent vertical line in a grid that we are working on. Now, I said that there's also a diagonal line, and that is correct. It's a line that perfectly intersects the origin at 45 degrees, right? So it would be a line that looks something similar to this over here. And when we reflect something over a diagonal line that is a perfect 45 degrees, it means we are actually completing both a horizontal and a vertical reflection at the same time. Now, again, we're going to take a specific closer look at all of this in next week's lesson when we go through some examples. But for now, we need to understand a lot of theory first. Okay. Now, there's nothing stopping my horizontal line from being somewhere down here, grade nines, right? This could be my horizontal line of reflection if I had a shape over here and I wanted to reflect it down here, right? Then it makes only natural sense that we have the option to move this horizontal line of reflection. Even though it's usually going to be our x-axis, it can be moved up or down to anywhere on the grid. All right. I hope that that makes sense to everybody. So that's everything that we need to understand about reflection for now. And yes, reflections do impact our coordinates. And that's what we're going to pay a little bit more attention to in next week's lesson. But for now, let's focus on the theory. Next, after discussing reflections, we have rotations. Rotations is quite an obvious one, guys. So, rotations involve turning a shape in a specific direction by a certain number of degrees. Right, guys, please take notes and let me know if you have any questions. There is a fair share to write down. Hi, guys. So, when we decide to rotate a shape, grade nines, we generally have to move the shape by a certain number of degrees in a certain direction, right? Movement exists in at least a 2D plane, which is why we need to know about direction and the degree to which we move in a specific direction, right? Now, if we're turning 90 degrees, it means we are looking at a quarter turn. A 180-degree turn is a half turn. 270 degrees is a three-quarter turn. And finally, 360 degrees is a revolution or a full spin back to the original direction. Now, when we rotate a shape, it doesn't mean that we get to move where the shape is, right? If I tell you to turn around, it means that you're going to stand where you are and just turn directionally. When I tell you to turn around, you don't move four steps to the left and two steps backwards and then turn around, right? Rotating is independent. There's nothing that says, guys, later on that we cannot combine these transformations so that I rotate something and I reflect it and then I move that reflected shape, right? It is very possible for us to chain these transformations together. But before we can understand how to do them in combination, we need to understand how to do them in isolation, right? On their own, one at a time. Okay. Right. So quickly write notes on all of this, please, guys. If you do have questions, you know that I'm here to answer them. And we've got two different transformations left that we need to write some notes on. Translation and dilation or scaling. Right. Next, we want to talk about translation. Translation is a bit of an odd word because it's not as representative as rotations is at first glance. Rotations quite clearly means to rotate, turn, or spin something. Translation, however, when you think of translation, you might think of translating between languages, right? Going from one language to another. In the world of maths, grade nine's translation refers to the movement of a 2D shape in a 2D plane. So, taking a 2D shape and moving it around a grid, essentially. I haven't seen any questions yet, so I'm going to assume that everyone's okay for now. I'll give you 1 more minute to finish copying, and then we'll take a look at translations. Okay, let's move on to translations, grade nines. The next transformation that we need to understand for the sake of transformation geometry, like I said, translations. Right, so the translation or a translation refers to the movement of a 2D shape from one location on a grid to another by vertical and horizontal movement instructions, usually measured in units. Okay, now as we have gone through all of these different transformations, guys, they've there's been a sentence in each individual transformation that describes what parameters we have when we complete that transformation. So, for example, looking at translations over here, we know that translating something means to move it around a grid, but translations may not affect the size of the shape or the direction. So if I'm given a square over here, let's call this A, and I need to move it to point B, I need to make a copy of this shape in terms of its size and direction. I may not all of a sudden change my shape to look like this, right? Change its size to be bigger and its direction to rather be offset by 45 degrees, for example. Okay, it needs to maintain its original size and direction. It's only the location of the shape that must move. Okay, so now, guys, if for example I am given a point over here, and this point exists at 6, 4, and I've been asked to move this point, let's say 3 units down and 5 units right, you would then work on a grid to move 1, 2, 3 units down and 1, 2, 3, 4, 5 units to the right for the new location. And if this is point A, this would now be A accent essentially. And you would be able to determine the new coordinates as 3, 8. And that's what we're going to have to focus on in our next lesson next week when we try and focus on finding the new coordinates of a shape or a point after transformations have been completed. Right. So quickly take a second to copy that down as well, guys. And once we are done with this, we will look at the very final kind of transformation, which is called dilation. Right, you've got just under 2 minutes to finish copying very quickly. And if you have any questions, please let me know. Just under 1 minute left, grade nines, to finish copying. Then we're already 3/4 of the way through today's lesson. Okay, guys, let's move on to the final kind of transformation. We just want to talk about what it means to dilate a shape. Okay, now this is where the work in relation to the grid that we've been talking about since the beginning of today gets a little bit more complicated. So, what does the term dilation refer to? Dilation talks about changing the size of a shape without changing its direction or position by what we call a scaling factor. Okay, so let's quickly write one or two notes and then I'll talk you guys through what we've written down. It refers to the changing of a shape's size by a scaling factor. Right. Changing the shape's size by a scaling factor. Now, it's important to keep in mind that this refers to enlarging a shape and, sorry guys, one second. Right. Enlarging and shrinking a shape. Okay. Now, again, what are those parameters that we need to keep in mind when working on dilation? Dilation should change a shape's size, but it may not impact the direction or position of a shape. Right, so let's talk about this concept called a scaling factor. So, when we talk about a scaling factor, if I want to take a square, for example, that is this big and change it to a square that is much bigger than that, if my original square had a side that was 3 units long and my new square has a side that is 9 units long, we can determine that we have a scaling factor of 3 because we have tripled the size of this square. Each side was originally only 3 units long, whereas now it is 9 units long. If I were working with equilateral triangles and I decided to shrink my triangle, originally it was 7 units on each side, and now it is, or let's rather say 8, and now it is only 2 units on each side. How do I move from 8 units to 2 units? Well, our scaling factor is now a quarter, right? So this scaling factor is a number that tells us the degree to which the size of a shape has been changed. What else do we need to know about the scaling factor? Well, it would be pretty good to understand how to calculate the scaling factor. So, how do we identify it? We take the length of the new side of a shape and we divide it by the length of the old side, the unchanged original side of the shape, right? And please keep in mind that if I use the left-hand side of this square, I need to use the same newer measurement of the left hand of that square, right? I cannot pick to use the bottom of shape number 1, but the top of shape number 2. And the reason for this is that when we start working with more complicated shapes that are not as symmetrical, if you do not use the corresponding side, you are going to get the wrong answer for your scaling factor. Now, how do we interpret the scaling factor? Well, if our scaling factor, the number that we get, is larger than 1, the shape was enlarged. And if our scaling factor is smaller than 1, the shape was shrunk. Okay. So, for example, over here, I'm going to go through this quickly for these two examples that I've given you, but I just want to use some more proper shapes. I will use the same values, so if you were copying, please don't worry. Right. If I have a square that originally had sides of 3 units and they now have 9 units on each side, how do I determine the scaling factor? Remember, we're going to take the length of the new side, which is 9 units, and divide by the size or the length of the old original side of that shape. So if it's become 9, but it was originally 3, we are essentially working with a fraction of the after value divided by the before value. 9 divided by 3 gives me a value of 3. And if my scaling factor is larger than 1, my shape was enlarged. Is that the case for this section over here? It absolutely is, right? My shape has definitely gotten bigger. But if I have a triangle like this over here that was originally much bigger, and we decided for some other reason to make this shape smaller, right? Again, let's say I had sides that were originally 8 units each, and now they've shrunk down to 2 units each. We're moving in this direction. Our shape has been dilated, but that's not good enough. We need to know if it's been enlarged or made smaller. So we're going to go ahead and calculate our scaling factor. Remember, we take the new divided by the old. The new side is 2 units long, while the old side was 8 units long. And if we go ahead and simplify that fraction, we have a scaling factor of 1/4. If you wanted to change this into a decimal, it is 0.25. Is 0.25 less than 1? Yes. So it means that our shape was made smaller. And looking at the pictures, that's quite clear. Yes. But guys, there is nothing to say that your teacher has to give you a visual aid. You might just be given the numbers and asked if a shape was dilated or, sorry, if a shape was enlarged or made smaller. And you need to be able to tell me whether or not it was made smaller or bigger just by calculating the scaling factor. Okay. Now, this is quite important because when we decide to go and work on a grid, my coordinates are going to change quite a lot. And understanding how we move from the original coordinate, sorry, to a new coordinate once the shape has been dilated takes a little bit of practice. And like I said, that's what we want to focus on in next week's lesson, where we take these 4 transformations that we now know about, uh, reflection, rotation, translation, and dilation, and see how these processes affect our coordinates in the context of a Cartesian plane. Guys, it's not super difficult to understand that a reflection means a mirror image, a rotation means to turn, translate means to move, and dilate means to resize. But I could have just told you that right at the beginning of the lesson. The catch is that you might not know that rotations do not allow you to change the position of a shape, or the dilations mean you may not change the direction or the position of a shape either, but you can only change its size. Okay, so there's a lot more to each of these processes that we need to just be made aware of, right? And it's things that you might think are super obvious, but if you get tested on dilations in a test and you move your shape, you lose all of your marks, grade nines. And that's because you missed the fact that a fundamental feature of dilation is that location must remain unchanged. Okay. Now, some of you might have thought about this already, but I just want to point it out. We have these 4 transformations: reflections, rotations, translations, dilations, and each of these have been studied separately now. But again, there is nothing saying that these 4 transformations cannot be daisy chained, right? May not be completed simultaneously, so that while our shape is changing direction, it's also expanding, right? And this seems like such a trivial topic to study, guys. But if you ever want to go into anything, let's say, for example, mechanical engineering, this is an incredibly important topic. A lot of subtopics within science, have got to do with these independent transformations. Material engineering, nuclear engineering, lots of things related to physics. All of these topics or industries use this to some degree in their work. Okay, so no, it's not hard work. No, it's not going to be 80% of your exam, but do you need to understand it? Yes, you do. Okay. Things in the world do not stand still, grade nines. Things change and morph. So we need to understand how to deal with dynamic behavior. How do we deal with things that are going to be changing? All right. And this is our first little very basic peep into that understanding. All right. Grade nines, unfortunately, guys, that's it for today's lesson. During the course of today's class, I didn't see any questions from anybody. So I'm going to assume that everyone understands what I've been through. Um, if you guys do have questions, you know that you are more than welcome to bring them to our next lesson, which is again going to be next week from 5 to 6 in the evening on Wednesday evening, right? So I hope that I'll see many of you guys there. Please remember that you can go and use iRainbow to practice all of this work, right? If you go into iRainbow, into the section called Geometry, you can then look at the subtopic named Transformation Geometry and go and test yourself on your understanding of this. Not only the theory, but the practical application if you have learned about this a little bit in class. Okay. But grade nines, that's it for today, guys. I hope that you guys have a fantastic evening further, and I'll chat to all of you again next week. If you have specific questions, please bring them to next week's lesson, and I'll try and answer them for you. But guys, until then, best of luck with all of your tests and exams, and I'll speak to you on Wednesday. All right. Thank you so much, guys. Enjoy.